First of all, I want to thank the organizers for giving me the opportunity to present some of our work. That's not work I do by myself. On the contrary, this involves a large team. It's actually an international collaboration. That's because we do these experiments at user facilities such as synchrotrons, the Advanced Light Source here in Berkeley, California, or the European XFEL in Hamburg in Germany. So this is where you need manpower and also brain power. So it's a collaboration of many scientists from the experimental side, but also from the theoretical side. And in this talk, I want to take you to the other side of chemistry, of photochemistry. This is really about fundamental dynamics in small systems. We are really looking into dynamics and mechanisms and processes that underpin the photochemistry. And especially important here is the coupled motion of electrons and nuclei when you shine light on just simple systems. I'm actually a scientist with an atomic physics background. I never made it to chemistry because I got stuck with these fundamental questions. I was always wondering, if I don't understand it in a single molecule, how can I deal with the big molecules and do real chemistry? So that's why I devoted my time and my science to these fundamental questions. So in this talk, I want to talk about timing dissociative dynamics of small molecules and dimers with internal clocks applying coincident particle momentum imaging. That's known as COTRIMS, or it's also reaction microscopy. So this method combines microscopy and spectroscopy, and we are able to visualize and understand the kinematics and dynamics in single molecules. So we prepare these single molecules in a supersonic gas jet, which goes from the top here to from the bottom here to the top. So molecules come out in a DC stream, and then we shine in the light as pulses, and these can be pulses from a synchrotron, from a laser, or free electron laser. And once you do that, you ionize the molecule, you expel electrons, which are guided to one detector, and then the molecular structure dissociates. So then ions come out, and we guide this with an electric field to the opposite side of the spectrometer, where we have another dedicated detector. So like throwing a baseball, we can measure the time of flight this particle was in the air and where it landed on the detector. And with this, you get an idea about the momentum vectors these particles had when the ionization and fragmentation happened. And that's very powerful because it helps you to put yourself into the molecule. You can sit in the molecular structure if it's small enough, and then you can see how electrons are leaving the structure while the structure is evolving during the fragmentation process. So this is very powerful. The downside is it really works very well only with small systems, and this is what we are after now. But I will give very highly detailed insight into these mechanisms. All right. So it's all about electrons in motion. We know that coupled electrons and nuclei are important for molecular dissociation processes. Electronic transitions, like this one, they initiate dynamics on the potential energy surfaces we know in chemistry. And the dream is that we can film molecular movies. That's what we want to see. We want to see the coupled electronic nuclear motion. Once the electron moves, the structure beneath it, the nuclei will notice, and it will change. And that gives feedback to the electrons, and they will act accordingly. And this will all happen on very short time scale, ultra fast time scale, usually in the femtosecond range. And this is what we try to do, and what I try to present during this presentation. It's all about electronic processes that are happen during nuclear dynamics. And in particular, I want to talk about changing charge states during sequential dissociation. And then we want to time on these fundamental timescales. Processes like electron transfer that can happen via spin orbit coupling. We do this in water molecules. You want to understand and time the interatomic decay of transient states. If we do this in a small environment, it's a neon-krypton dimer. So you have a neon on one side and krypton atom on the other side. And then in the last part, I will talk about the charge up in a sequential ionization in oxygen molecule, where we did an experiment at the European XFEL, where you have so much light that you can absorb 2 X-rays at the same time in the same photon pulse. So these are challenging tasks. We have to isolate reaction channels in the molecules, of which there can be many. And then we have to trace the dissociation pathways of this. There can be also several that can happen on the potential energy surface. The molecule has many choices. And then we want to time these fragmentation steps. And we don't want to do this with conventional pump and probe spectroscopy. We will do this with internal clocks. We can sometimes do that if we apply simple pictures like these fragments, these particles, these electrons which are moving are in principle simple Coulomb potentials, which we can treat almost classically. And then with our highly detailed insight, we can set up internal clocks which are very powerful and actually pretty precise. They can beat out pump and probe experiments. Okay, so let's shine some light into matter. There can be a manifold of reaction, as I told you. Just take a photon of 55 eV and let's give it to a water molecule. The water molecule has many choices. Most of the time you will have single ionization, and the water can form a stable cation, or it can break up in 2-body or 3-body dissociations. That has been studied for many years. And within the recent years, we were happy to provide some detailed insight into the double ionization, which is only 0.5% of all the ionization events that can happen. You won't find a stable dication here, but you can also have 2-body and 3-body breakups. They can be direct or happen in a sequence. You can have two-body breakups in a row. You can have symmetric and asymmetric stretch between these OH bonds. So we could fill the literature with some detailed insight here. And we thought, okay, we're pretty much done here. But then a colleague of mine, Thomas Weihnacht, he approached me and said, you know what, I'm doing something similar, but I'm not using only one photon. I use a laser, and I will bring in many photons at once. And I see a reaction channel which is not listed here in your table. And this is the one where you produce a proton, an oxygen ion, and a neutral hydrogen. And this is a player in my strong field ionization. I'm surprised it doesn't show up at all. Can you dig deep and tell us if it's happening and what the mechanisms and transition and dynamics are behind that? So we thought, okay, this is no problem for us, but the trouble starts already finding that beast. As I told you, there are many reaction channels that can happen, and you need observables to dig those out. And one important observable is the so-called PPCO spectrum. This is the photo-ion coincidence spectrum. It measures, or what we have measured here is the time of flight of the second ion we detect versus the time of flight of the first ion we detect. And that's very powerful because we see all these lines and islands here. And these are the many reaction channels I listed in that table. And this is a logarithmic scale. And the one my colleague was after is hidden here. It's very little. It is only 0.5% of all the photo double ionization events. So it's very rare. In the next step, we now have to understand, okay, how are actually these reaction products created and what kind of ionization mechanism is behind that? And since we measure in coincidence electrons and ions, we can plot the measured electron energy of the electron in the continuum versus the kinetic energy release of all the fragments that then exploded. And we can see that we produce a very low energy photoelectron here. That's actually from outer ionization. and this is corresponding photoelectron. Remember, it's a double ionization. You have an outer ionization electron and then the photoelectron. So that's one mechanism, and the rest here is the direct photodouble ionization, where you have emitted two electrons at the same time. And in the following, I want to pick up those events and now try to figure out, okay, what actual states are we talking to? When the photon comes in, what dication states are actually populated? And for this, I print another, or not another observable, and that's the sum of the two electrons I measured versus the kinetic energy release. What this does, practically, it probes the potential energy surface of this dication. Potential energy surfaces are actually hard to come by for molecules, even for simple molecules like triatomics. It's not easy to calculate, and very often we have to look in the literature and deal just with cuts of or special cases of these potential energy surfaces, which for instance here is a special case. That's the potential energy curves of the Wada dication for a special case where both OH bonds, they stretched symmetrically. So we stretch them symmetrically, and that's how you see how you can bring a molecule to dissociation. The final states we are after are the blue and green dashed line. You see these are these triplet states of the reaction channels we are after, producing an O+, a hydrogen, and a proton. But if we look into our photon energy, if we bring it in, 55 eV is not enough to directly get access to these dication states. And that's also what our observable here tells us. We must do this in an indirect way. It appears that we first produce a reaction channel where we produce two protons. We land on these singlet states here. Then we have dynamics taking place, the dissociation starts, but at one point there's a crossing here, and now the molecule, the dication, has the choice where to go, and some small part will make the transition to our desired triplet states. This can only happen by changing the spin, so we need some spin orbit coupling, but then it can produce the dissociation, and we end up with the limit we are after. So this is an indirect process that can happen, and we want to find more evidence for that. And for this, we plot another important observable. That's the conformation map, which is made up of the kinetic energy release of heavy particles of this fragmentation as a function of the angle between the two hydrogens in the molecule. And it appears we have two contributions here. One is this triangle here, which let's call it the lower kinetic energy release part. And if we look at the relative angles between the fragments, meaning the fragments between the proton and the oxygen ion, and the proton and the hydrogen, and the oxygen plus and the hydrogen, we see this spectrum here, and it tells us that the dication actually opened up. So when we hit our water molecule, which had 105 degrees of bond angle, it appears when we shine in the photon, the bond angle opens to something like 150 degrees, and that supports what's sketched out here, so that we first have a direct three-body breakup with a symmetric stretch where we produce two protons, and then we must have a charge transfer. One of the proton looks back and decides to steal an electron from the oxygen atom and ionizes it. Within our resolution, it's also possible that we have a competing sequential dissociation happening at that point. We are looking into that, so this is still under the microscope. So let's turn our attention to the other part here in the conformation map, where we have the high kinetic energy release. And here the relative angles of the heavy fragments look rather different. Now the dication doesn't want to open up, it looks like the dication wants to close. It wants to from 105 to 90 degrees. So we took the information we got in and we tried to figure out what's happening here. And what we believe is happening is that we actually have a sequence of processes taking place here. So you shine in the photon, then you have a quasi-sequential breakup where you first bring out a proton and you leave an OH plus behind. Now the molecule stretches asymmetrically, and again at one point this first outgoing proton looks back and decides to steal an electron from the oxygen atom. We must have a spin-orbit coupling to make it to these states here, and then we have the final reaction products we are after. To find more evidence for what we here propose, we change from the molecular frame to the native frame. So we not can only sit in the molecule, but we can also follow the fragments we are making throughout this sequence of reaction steps. And with this, we are now able to look into the first step, where we plot the breakup axis, which is defined by this breakup, where the proton goes in one direction and it leaves an OH plus behind. And we plot this with respect to the polarization of the incoming light. This is the angular distribution we show here. So these black dots show the probability of how the breakup axis is orientated with respect to the polarization. So most of the time we see that the proton goes along this horn. Of course, it goes also along this one and this one. It's just folded, it's symmetric. But in principle, it means that one OH bond in the molecule likes to be parallel to the polarization when it absorbs the photon. Okay, that might make sense. So now let's look at the second breakup axis, where we leave that OH plus behind, and after a time it decides to fragment as well. And that's what we plot here, again with respect to the polarization. We see that this axis has rotated a bit. It has not rotated a full turn, otherwise we would see a red circle here, but it has rotated a little bit. That would make sense because the proton, the red particle, left the system, and when it does that, it gives a recoil to the left behind OH plus ionic fragment, and that induces a rotation. And actually, I told you before, we measure the momenta of these outgoing particles. We measure the momentum here of this red hydrogen, and it's about 8 atomic units. We see that this fragment axis rotated about 27 degrees, and assuming Coulomb potentials at play, that tells us that the time that elapsed between these two steps is on the order of about 10 femtoseconds. But we still have to figure out if we can do the last step. Can the outgoing proton look back now and steal that electron? We need to make this electron transfer happening. We need a spin-orbit coupling. So for this, we sat down and took all the information from the lab frame, from the molecular frame, from the native frame. We took all the kinetic energy release. We measure the relative angle between the particles, and putting in the knowledge that we have Coulomb potentials at play, we can translate them into internuclear distances. And then we learn that the asymmetric stretch we assume is actually not that strong. The OH bonds, when this molecule dissociates, only differ by 1 atomic unit. That's not very much. But this information now is helpful to approach our theory team and ask them, okay, can you give us a special potential energy surfaces where we can look at this dynamics? So can you plot potential energy surface where you plot the angle between the two hydrogens in the water molecule on one axis, and this asymmetric stretch between the OH bonds here on the x-axis. So it's a very special case for the main player, the main dication state we populated, which we found out earlier. And then we take our milestones here and put them on this potential energy surface and figure out if we find a dissociation pathway which goes downhill, which would tell us, yes, such a fragmentation can take place. And yes, if we find this pathway, we now also have knowledge about the gradient of this potential because the theory team calculated it for us. And again, if we assume Coulomb potentials at work of these particles, we get an idea about the time between these breakup steps. We also learn that our transition or the stealing of the electron has to happen here at that last milestone. It has to happen when one OH bond stretch is about between 4 and 5 atomic units. And now theory can zoom in and they can say, oh yes, if we look in detail and scan the OH bond going from around 4 atomic units to 4.5, we see how these two dication states, the triplet and the singlet state, approach each other, and they form a seam for efficient spin orbit coupling, which is necessary that for the electron to hop over from the oxygen atom to the proton and neutralize it. So in summary here, yes, we found our outlet, the spin orbit coupling is happening, and the electronic transition can take place. So this was all about electron transfer during a dissociation in water molecules. In the next part, I want to focus on photon transfer. And we want to investigate this in the decay of a transient state. And we trace the evolution of interatomic Coulombic decay in neon-krypton dimers. And that's sketched out here. So there's the neon and there's the krypton. They can form a dimer. And now we shine in a photon and we emit an inner shell photoelectron. And then an outer shell or valence electron will fill this hole. And this releases some virtual photon. It can travel to the other side and emit here on the krypton side another electron, a so-called ICD electron. Electron which was formed by the interatomic Coulomb decay, which is now following, because now we have created a neon plus and a krypton plus. The electrons are gone. That means this dimer will Coulomb explode on us. So we do that at the synchrotron in a rather clever way. We shine in our photon just above threshold. That creates this first photoelectron here with very little energy. There's only 100 millieV in the continuum. So it's still hovering around, while at the same time, nuclear dynamics is taking place. We have ionized the neon krypton dimer, and it will actually contract on us. And at one point, the Coulombic decay, ICD, will happen. The virtual photon transfer takes place, and it emits now this ICD electron. And actually, this ICD electron is rather fast. It has 10 eV in the continuum. So it will overtake our photoelectron. And at that point, the photoelectron looks back at the neon krypton dimer, which was a neon krypton singly ionized, but it now has changed to a doubly ionized neon krypton dimer because the ICD electron was emitted and overtook the photoelectron. That means the Coulomb potential has suddenly changed, and the photoelectron will now be decelerated. And it will explore a shift in energy. And again, thinking about in a simple picture that these particles behave like Coulomb potentials, we can relate this shift in energy to a time that happens. We can do this, so we can simulate that classically and relate the shift in electron energy to a decay time for specific photoelectrons with specific energies in the continuum. And I told you, we measure the ions and the electrons at the same time in coincidence. That helps us to relate the electrons to the ions, meaning we can relate the kinetic energy release of the ions we measure to the shift in electron energy. And this in turn relates to the decay time. So we can make a plot like this, where we plot the decay time as a function of kinetic energy release of the dimer here. And then we just make projections of this spectrum slices, which we now stitch together. And we have a little molecular movie. That's what you see here. This evolving structure is the excited dimer as it contracts on ultra-fast timescale. So this is the internuclear distance between the neon and the krypton. Once we took the photoelectron away, it contracts, and it does this on ultra-fast timescales. You see this clock ticking here. That's important because this internuclear distance is critical for ICT to take place. Here's an overview of that movie. Again, it's the internuclear distance as a function of time. We see this contraction. We also see nice agreement with theory of the group in France. But maybe more importantly, it also tells us a bit about our resolution, which is very good in space, but also in time. And it outbeats experiments that do traditional pump and probe. So this movie is normalized to the maximum of the peak you see here that contracts, but we also measure the relative yield. And with this, we can answer the question, what's the survival probability of the excited dimer? And that's what's plotted here. The yield decreases very quickly as a function of time. After 150 femtoseconds, ICD in neon krypton is pretty much over. And that's much faster than previous measurements on helium dimers, which are bigger, but also their dynamics is 100 times slower. Okay, now to the last part, we want to keep on exploiting Coulomb potential for timing dynamics. And we do this now in a charge up and a sequential ionization. We now went to the European XFEL, where you have very, very intense light beam that can deliver X-rays. And it delivers the X-rays in a pulse, and we shine it into an oxygen molecule. And it has, the X-ray pulse has so much intensity that we can absorb 2 X-rays. And then again, many reactions can take place. But in the beginning, we focus on the reaction which produces an O+, O3+, 2 photoelectrons and 2 Auger electrons. So how is that taking place? It's sketched out here. We shine in the light pulse, the first X-ray is absorbed, the photoelectron comes out. We made the O2 oxygen molecule a singly ionized ion here. We create an O+, but we emitted a K-shell electron. That means Auger decay is happening. Some other electron will fill this hole, and it will spit out another electron, and then you have a charge up. You created an O+ on each side, and now a Coulomb explosion starts. These 2 ions, they want to repel each other. But I told you the light pulse is very intense, so we have a probability that we absorb another X-ray, meaning we kick out another photoelectron. And this means we charged up by another charge state, so we created an O2+ and an O+. And this photoelectron now is emitted and illuminates this molecular ion from within as it Coulomb explodes. But again, it's another K-shell electron. And so an outer valence or inner shell valence electron, they will fill that hole, and an Auger decay is happening. That means we get another charge up. We end up with an O+ and an O3+ that accelerates the Coulomb explosion, and the molecule explodes underneath us. That's again sketched out here in these potential energy curves. This is the absorption of the first X-ray. We spit out that photoelectron. Now we have the Auger decay happening. So we create an O+ and an O+. That's the potential energy curve. The dissociation or the Coulomb explosion starts, and it will do this to a certain internuclear distance. And this contributes to the first part of the kinetic energy release we measure. And after some time, of which we have no control over, the molecule absorbs another X-ray. So we have another sequence like this. Again, we absorb an X-ray, kick out another photoelectron, we create an O+ and an O2+. Auger decay happens. So we have another charge up, and we finally land on the O+, O3+ potential energy curve, and that gives us the second contribution to the kinetic energy release. And kinetic energy release is something, again, we want to exploit as an internal clock. We think of the particles as Coulombic potentials in motion pretty much. And we use this kinetic energy release now to look how the second photoelectron that is emitted in this simple reaction is emitted in the molecular frame. And that's what's plotted here. So the O3+, which we measure, went to the right, and the O+ we detect went to the left. And you see the emission pattern, the probability of the second photoelectron to be emitted with respect to this molecular axis. You see this here, and now we plot this as a function of the kinetic energy release. So the kinetic energy release decreases along these panels, and we can relate this kinetic energy release to an internuclear distance and to a time, because we exploit that Coulomb potentials are at work. So we can give them some sort of timestamps like 7 femtoseconds, 11, 14 femtoseconds, and we see the evolution of this emission pattern on ultra-fast time scale. Again, we can sketch this together as a little movie here. So as a function of time, you see as the molecular ion is kind of expanding, you see how the emission pattern of this electron is changing because the molecular structure has changed. So what we in principle did here, we did some time-resolved diffractive imaging of a Coulomb explosion without pump and probe. We used our internal clock. And this apparently worked very well. The red line is not a fit through the data. It's actually some intricate quantum mechanical calculation here. But it also tells us that our approach and our idea of Coulomb potentials in motion works quite well. Okay, we want to further exploit this Coulomb explosion model and solve now the Newton equations of motion. And we do this for another reaction channel that actually takes place. You can also create an O3+ and an O2+. So another reaction channel, but this is interesting because it can happen in two ways. Again, we absorb two X-rays in oxygen molecules. So we now absorb the first X-ray and you emit a photoelectron and an Auger electron. So you create an O+ and an O+. And now you absorb the next X-ray. And you can again create a photoelectron, but you can also shake off another electron. It's called a shake-off electron. And then you have an Auger decay. That means you end up with a highly charged state, O3+ and O2+. You can also reverse that sequence. So the first X-ray not only emits a photoelectron, but also it shakes off another electron, and then you have the Auger decay happen. So 3 electrons went out, meaning you create an O+ and an O2+ in the first step. So that's it's higher charged than this other reaction route. And then you absorb the second X-ray, and you can again kick out a photoelectron and have an Auger decay, and you end up with an O3+ and O2+, meaning the same reaction products as the upper reaction up here. So you have 2 ways to generate a 5-fold ionized oxygen molecules by absorbing 2 X-rays. And you can solve the Newton equations, and you can relate this kinetic energy release between the ions here we measure and relate them to the internuclear distance. And you can also relate the time to this internuclear distance. And that's what's plotted here. So here is the time of this Coulomb explosion as the function of the internuclear distance, or we can also relate it to the kinetic energy release. And this is what this tells us. After 17 femtoseconds, both reaction pathways, regardless if it happened this way or here, like this way in the second row, both of them, they reached 39 electron volts in kinetic energy release. But we see that the dissociation route, which created a higher transient charge state, an O+ and an O2+, reached an internuclear distance of 6.5 atomic units, by the other charge states, which only had an O plus and an O plus on each side and was lower charged, had only an internuclear distance of 4.5 atomic units. Makes a lot of sense because we know the higher the charge states, the faster and the more these ions repel each other. Okay, with this we can summarize. So I talked about state-selective dynamics and correlation in polyatomic molecules. We monitored the changes of charge states during sequential dissociations. We traced moving electrons during structural changes of the molecular structure, and we timed electron emission in ionization sequences, the electron release in the decay of transient states, and electron transfer during molecular dissociation. Here again, I list our timing modalities. We didn't use pump-probe, but we used our internal clocks, and they were based, for instance, on Coulomb explosion imaging. Then here in part B, they were based on the post-collision electron energy shift, or we used the fragment angular distribution. There are other scenarios or other tools we can think of. One, for instance, is the molecular frame electron angular distribution. And with this, we close the loop to water. We go back to the photodouble ionization of water in the beginning. This we did some years ago already. We double ionized the water molecule, a photoelectron went out, and we had a two-body breakup. A proton was expelled, and then we made an excited OH fragment. And this excited OH fragment, after some time, decided, oh, I cannot hold on to that electron. I auto-ionize, and I kick out that auto-ionization electron. And this is what's plotted here. You see the emission pattern of this auto-ionization electron with respect to this breakup axis, the OH plus on this side and the H plus going on this side. So there is some clear probability for the outer ionization electron to be emitted along that proton. And again, we can treat this classically, and we can classically model this electron diffraction we see here for different internuclear distance. We can assume. We don't really know when it's happening, but we can model that. So we can plot the flux or the fraction of flux in this nose here, or the asymmetry parameter of this distribution as a function of electron energy. Now just assuming as a parameter different internuclear distances. These are these lines plotted in here. And then we compare them to what we measure. And we see that we have good agreement if the internuclear distance between the OH plus and the H plus when the auto-ionization happened was something like 800 atomic units. And we measure a kinetic energy release of 3 electron volts. And within our Coulomb potential molecule, we can relate this to a time between the two steps where we emitted the photoelectron and the auto-ionization electron. It appears that 2 picoseconds have elapsed. And that's an interesting clock mechanism we now want to actually apply to some more complicated molecules like methanol in the future. All right, with this, I'm at the end. There are many people to thank, actually more than I can list here. Many groups and scientists at work. It's an international collaboration, as I pointed out in the beginning. But I want to thank mostly the students, which are labeled here with the arrows. They did all the hard work behind the scenes. And of course, I want to thank the sponsor, the Department of Energy, that sponsored the science here. And of course, I also want to thank you for your kind attention. And this is the end, and I'm happy to answer any questions, but you can also contact me here via email. Thank you.